Okay, this video I'm going to go through a scenario with the network, and we're going to subnet it using VLSM. Now, you might have seen in some of the previous lectures to this that I've talked through how to perform subnetting in VLSM, but until you actually apply it to a scenario, it's difficult to visualize how this is going to work. So what I'm going to do in this session is just walk you through a subnetting scenario. So let's go through what this paper has to say. So in a typical address allocation scenario, you'll be given a topology, a set of host requirements, and a starting address range, and you have to calculate an addressing scheme which will provide you with the most efficient allocation of addresses using in VLSM. So I'm going to go through this example. Okay, so before we start, we need some rules, and these rules always apply to subnetting that we do. The first one, and you've seen this in previous lectures, is an IP address has two parts, the network and the host portion, and the subnet mask determines where the network portion finishes and the host portion starts. The IP address and the mask are 32 bits, 32 bits long. Okay. The second thing that always stays the same is the network address has three parts. The network address space has three parts. The network address, which is shown in red here, which is the very first address in the range. The broadcast address, which is the last address, and the host range in the middle, which is this white bit here. The network and the broadcast are reserved, so we can't actually assign these to hosts. Hosts are things like PCs, router interfaces, switch management interfaces, and so on. So you can't assign a network address or a broadcast address. These red ones here are reserved, and you can't use those for hosts. But anything in the host range can be used as an address for a PC, a server, a router, and so on. The other thing to know is the network address is defined by all the host bits set to zeros. So binary zeros for the host bits, and binary ones for the broadcast. Subnets are created by borrowing bits from the host portion and moving them to the network portion. Okay, and this has the effect of creating more subnets, but each one will be smaller in size. So in effect, we're breaking down the network into smaller chunks by moving bits from one part to another. The number of subnets created will be 2 to the power of n, where n is the number of bits borrowed. So it's the binary number system, so it's 2 to the power of n, and how many bits you borrow will give you how many subnets you actually create. The number of hosts is 2 to the power of n minus 2, where n is the number of host bits. The reason it's minus 2 is because you've got 2 reserved here, network and broadcast, so only the host range can be applied to hosts. So you lose 2, hence the minus 2. So these n represents the number of bits. Okay, so if we borrow 1 bit, sorry, if we don't borrow any bits, it will give us 1 subnet, which makes sense really, because we haven't borrowed anything. The subnet's a whole subnet, it's not chopped in half or anything. If we borrow 1 bit, then the subnet's chopped in half. If we borrow 2 bits, it's chopped into quarters. If we borrow 3 bits, into eighths. 4 bits into sixteenths, 5 bits into 30, there's 32 subnets, 6 bits 64 subnets, 7 bits 128, and so on. You can see the pattern here. Basically these numbers are doubling each time. For the host portion, because it's 2 to the n minus 2, obviously if we if we have 0 host bits, then you're not going to have any network at all. If you have 1 host bit, which is pretty much useless, then you'll have no host range, because pardon me, you'll lose 2 immediately with the network and broadcast, and you'll end up with 0. So the first useful host bit will be to borrow 2, to have 2 host bits, and the remainder is network. In other words, a /30 mask, where 30 of the hosts, 30 of the bits are network and 2 are hosts. And as you can see, the more host bits you have, the larger the subnets get, but you have less. You'll have less subnets. So here's the scenario we're going to walk through. It's a 3-router scenario with 2 WAN links between the routers, and we're going to have 4 LANs with 40 hosts, 25 hosts, 70 hosts and 25 hosts, and then we're going to have a LAN up here with another 35 hosts. And we've drawn the table out here. So the HQ network, which is the router at the top here, is 35. We've got site 1, which is this router and the LAN here. Site 2 is this part here, and then we've got the headquarters to site 1 WAN link here, and the headquarters to site 2 WAN link here. And what we're going to do, we're going to be given an address range, and we're going to break it down using VLSM as per those requirements. Now, for this particular example, we're going to use a starting address of 10.00/8, which is a Class A, typical old Class A range private address. But you could use a 172.16.00/12 as a start, or you could use 192.168.00/16 as a start. They're all valid private addresses, but for this one we're going to use a 10 network. So remember, 10.0.0.8 means the first 8 bits of the network, and the remaining are hosts. So if we use our formulas in this table here, we can find that by default, without any subnetting, the network portion is 8 bits. That gives us 256 possible networks, because we have 8 network bits. And because we have 24 host bits, if we do a 2 to the power of 24, obviously minus 2, we haven't got that on the table because it would go off here, then that gives us 16 million hosts. That's a very big, large network. So what we're going to do is we're going to break this down per the host requirements here. Oops, pardon me. So the next stage is what we're going to do is we're going to subnet the network into equal chunks first. So what I usually do is I would subnet per site. So rather than starting to subnet using VLSM with individual hosts, I would generalize the address space per site, and then once I've got the site subnets, then further subnet that down with VLSM. So what we do, we'll assume, although obviously we can see that these have different number of hosts, what we'll do is we'll split it down per the host requirements. So we can see the headquarters has 35 hosts in total. Site 1 has 40 plus 25, Site 2 has 70 plus 25, and then we've got the WAN links, which are 2 hosts because there's only 2 addresses that you need, 1 at each end. So what we'll do is start with the largest site first and see how many addresses are required for that, and then from that we can look at the other sites. So we have 70 hosts and 25 hosts, so we're really going to need at least a block of 256 to support the site. You can assume that the site's not going to, in this example, you can assume that the site is not going to grow a great deal in the future. So you can say, yeah, a bit of room for expansion, but not too much. So in this case, we'll go with a block of 256 addresses. 128 will not be enough, really. So we'll go with 256. So minus the 2, that's 254. Okay, so that gives us 254 usable addresses for our largest site, which is sorry, this site here. Site 2 is our largest site. Okay, so from the table above, 8 bits is enough to do this. So step 2, what we need to do is calculate how many network bits that we need for that. Well, if we have 8 host bits, okay, so we've got 254 possible host addresses, then if we have 8 host bits, then the remaining bits must be network. So this green part here is the network portion, and that's the mask for the subnet. So the prefix or mask is a /24 because there's 24 consecutive ones in this portion here. And you can see how this is calculated. This is the binary here, and you can see there's 24 consecutive ones, and the one in red represents the last binary one in the subnet mask. So what we've done, we've started off with 10008 and we've subnetted into equal size blocks of 256. Because we've used 256 for the first network, then all the other networks are going to be 256 as well. So this is what we started off with here. So we started off with the 16 million addresses. This was before we started subnetting, and we've broken that down into these 256, 256, 256, and lots more. So basically, each site now is a 10.00/24. Okay. So after allocation, we can allocate the first batch of 256 to HQ, site 1, site 2. The WAN links are 256, and we have some spare subnets. We can work out how many subnets we have. There are 2 to the power of 13 subnets, and the reason we've got that figure is because we start off with a /8. Sorry, I mean 2 to the power of 12. That's a typo. Very sorry about that. I'll change that. 2 to the power of 12 subnets, which will give 496 subnets. There's 496 of these blocks. So plus lots more just means there's another 4,000 and odd. So we've got HQ. We know where HQ starts. It's 10.00/24. But then we want to work out where the rest of these start. To find out where the next network address starts, it's very easy to do. All you need to do is look at the mask, find out where the last binary 1 is, and that will tell you where the next network address starts at. So looking here, we know all our masks here at the moment are /24, which is 255, 255, 250. And if we break that into binary, we can see the last binary 1 here is the red 1, and in decimal that is a 1. Okay, that's a 1. So we know that in the third octet of each network address, it's going to increment by 1. And you can see that quite easily because that's going to be 10.0.0.0, 10.0.1.0, 10.0.2.0, 10.0.3.0, 10.0.4.0, and so on. So this octet here, the third octet, is incremented by 1 each time. And that number is taken from the subnet mask here. That number is what each network address of each one will increment by each time. And that rule applies using VLSM as we'll see in a moment. And here we have the address blocks for each site. So HQ is 10.0.0.0/24, site 1 is 10.0.1.0.24, site 2, 2.0.24, the WAN links 3.0.24, and we have spare blocks of 10.4 to 10.255.255.0, that's 24. There's 4,092 other networks that we haven't used, which are spare. Okay, so the next part we're going to do in part 2 here is each individual one of these we're going to break up further, we're going to split up further, but we're going to use VLSM. So these host requirements here, we're going to assume that these host requirements already include room for expansion, and we're going to break down those blocks of /24s further per the host requirements. So each of these address blocks gives 254 hosts. Remember, the network and the broadcast is reserved. However, this is still not efficient given the original requirements. So in the next section, we're going to further subdivide each block to provide more efficient allocation. Now, because we've already allocated these, we can go through each of these one by one and split it per the host requirement. So we'll start with HQ since that's the first subnet here. Just recapping with HQ, we've only got one LAN. We'll assume that there's only one LAN in this scenario because it's just a basic scenario. 35 hosts. Okay, so we look at our powers of 2, and we're interested in this this row here, and we need 35 hosts. So we need to work out how many host bits are required for 35 hosts. So we look down the powers of 2, and we think 30. No, it's not enough. Remember, -2 is the network and the broadcast that are reserved. So we have to go to 6 host bits to get the required number of hosts. Now we get 62, so we're going to have some over. Well, that doesn't matter because we can always justify that by saying, well, there's room for expansion. So we know that we need 6 host bits to specify our requirements. Okay, so if we have 6 host bits, which is this shaded portion here, then the remaining bits must be network, because the whole network and host portions must add up to 32. So what that means is we have a 26 network bits, or a mask of /26, or a mask of 255.255.255.192. And you might be thinking, well, how the hell did I get this mask? Where did this come from? Well, basically, /26 is the equivalent in binary is there's 255, there's 255, there's 255, and if you added these up in binary, it would be 128 plus 64, which gives us 192. So /26, 255, 255, 255, 192, and this binary string here all mean all the same thing. Now, as I said again, we need to find where the next network address would start, and the reason we need to do this is because we can calculate the host range and the broadcast address more easily. So again, what we do is look at the last binary 1 in the mask, find out what the decimal is of that, so it's going to be 64, and that means each next network address is going to increment in blocks of 64 in the final octet, because the last binary 1 is in the last octet, it will go up in 64s. And we can see this here. HQ starts at 10.0.0.0/26, because that's how many host bits that we need to satisfy our LAN. And then the next address range, which at the moment is undefined, would start at 10.0.0.0.64, because the last binary 1 in the mask is 64, so it would increment from 0 to 64. So basically, this is what we started with. This is our original HQ subnet, and it's divided up now into equal size blocks of 64. Now, if we wanted to, we could take the second block, for example, and break that down further into smaller chunks, but at the moment we'll just leave that as is. The next thing we have to do then for HQ is fill in the blanks regarding the broadcast and the host range. So we've defined the network address for the HQ LAN. We've already done that because we did it here, but now we have to define the broadcast. Now the broadcast, as I said earlier, is always the last address in the range. Okay, so it will always be the first address, it will always be the address before the next network address starts. Okay, so with that in mind, if the next network address starts at 10.0.0.64, then the broadcast is going to be just before it here, and it's going to be 10.0.0.63. Once we have the network and the broadcast, then it's trivial to work out the host range. It's going to be all the addresses between these values, so it's going to be 10.0.0.1 to 10.0.0.62. Okay. This host range here is what we actually apply to interfaces. So if we want to specify the interface addresses for the routers in HQ, the gateway here, and the servers, then we would use that host range. And then we have our unused subnets here, which represent these spaces here. Notice how it's incrementing, the last octet is incrementing in blocks of 64. 64, 128, 192. And all that comes from the last binary 1 in the mask, the /26, will determine how this increments. So that's HQ done. So let's go to site 1. So let's go back to site 1 and look at our requirements. Site 1 has 2 LANs of 40 hosts and 25 hosts. Now, when you're subnetting, you always start with the largest number of hosts first and then go down to the smallest. So 40 hosts, if we look at our table again, requires 6 host bits because 5 host bits is not enough. So we need 6 host bits. That gives us 62 possible hosts, which easily satisfies the 40 that we need. So 6 host bits means 26 network bits, which is exactly the same mask as we had for the last example. So it's the same mask, /26, 255, 255, 255, 192, on all 3 octets of 1s, 255, 255, 255. The 192 comes from here, 128 plus 64. Notice the last binary 1 in red is a 64, so that means the same pattern is going to happen again. We've got 64 for the first block. Remember, it starts from 10, 10, 0, 1, 0, site 1. So LAN A, which was our 40 hosts. So as you can see here, that's the 40 hosts. Next one we need to do is, let's go back, 25 hosts. So we've done this LAN here, sorry, on the wrong one. We've done the 40, now we're going to do the 25 for LAN B. So, LAN B, 25 hosts. We look at the table here, 4 bits is not enough, 5 host bits will satisfy the requirements. That gives us a few addresses left over. That gives us 30 usable addresses. We only need 25, so that'll be fine. So 5 host bits, that means the remaining must be network bits. That means we've got 27 network bits. The mask is going to be /27 for LAN B, and the mask is 255, 255, 255, 224. And the reason for that is we have 27 binary 1s. That's 255. That's 255. That's 255. 128 plus 64 plus 32 gives us 224. So you see the pattern? We do the same process again. Firstly, we calculate how many host bits we need for the number of hosts in the diagram. Once we've done that, once we know the number of host bits, we can calculate the number of network bits. That gives us our mask. That gives us our dotted decimal mask. There it is in binary. And the last binary 1 here in red, which in this case is 32, will tell us that the next network will increment 32 higher. So we saw from LAN A, that was 64. So it incremented from 10 to 164 for LAN A, and because LAN B subnet mask ends with a 32 for the last binary 1, then it's going to increment from 64 to 96. So from this, that we can now calculate the broadcast address of LAN B and the usable hosts in LAN B. So if we look at LAN A, we've already done that. So if we recap, LAN A started at 10.0.10.0/26. We know that it ended the next address range starts at 10.01.64, which is the start of LAN B, which is here. And we know that from the last binary 1 in the subnet mask of the /26 is a 64, so it increments from 0 to 64. And from this we can work out the broadcast address is 63 because it's 1 before it, and we can work out the host range is 1 to 62. So the host range here is 1 to 62. LAN B starts at 64, it will end at 96. Well, actually no, the next range starts at 96 because the last binary 1 is a 32, which we add on, so 64 goes to 96. That means the broadcast address of LAN B is 95, and the usable host range is 65 to 94. We've got some unused space here as well, which has not been subnetted, which will start at 10.01.96/27. So if we wanted to allocate that later on, we could do. So that's site 1 down. Let's go to site 2. Now you can recap from here that site 2 has 2 LANs, C and D. One has 70 hosts and the other one has 25 hosts. So slightly different requirements this time. So from section 1 we obtained a network address of 10.0.20 for the whole of site 2. We did that earlier on. And we're going to further split that for LANs C and D, which have 70 hosts and 25 hosts respectively. And we'll go through the same process again. So the first thing we need to do is subnet them in order of size, starting from the largest. So LAN C is 70 hosts. We'll start with that one first. We need to determine how many host bits are required for 70. So looking at our table again, 62 is not enough. It will have to go to 126 hosts, which is 7 host bits. So N is 7. So if we have 7 in the host portion, that means the remaining bits, remember this whole section must add up to 32, so that means we've got to have 25 network bits or a mask of /25. Okay, that's a decimal mask of 255.255.255.128. How do we get this? Again, there needs to be 25 binary ones. So there's 255, there's 255, there's 255, and there's the 128, which is the final binary 1. I've marked it in red because we're going to use that value to increment. So that in decimal is 128, and so from 10.0.20 the final octet will increment. The next address range will start at 128, higher than that, and we can see that here. So site C we've just subnetted. We have a start range of 10.120/25, which we've worked out here, and the next subnet, next LAN, this should not say site by the way, it should say LAN. The next LAN will start at 128 higher in the final octet, so 0 goes to 128. So now what we need to do is work out LAN D. Okay, now LAN D had 25 hosts. So using the table again, we look and find how many host bits we need. We need 5 host bits, because that gives us a total of 30, which is enough for our requirements of 25. 5 host bits, which means we have 27 network bits, because it always has to add up to 32. 27 plus 5 is 32. 27 network bits, or a /27 mask, is 255.255.255.224. How do we get this mask? Well, 27 binary ones, there's 8 of them, that's 255. There's 16, that's 255. There's 24, that's 255. 27 is there, and notice the last binary 1 in red will be a 32. It's got 128 plus 30 plus 64 plus 32 gives us 224. So because our last binary 1 is a 32, that means our network address that we got from the last calculation here will increment by 32, so it will go from 128 to 160. Okay, so we've now got the start range for the ranges after LAN D. So now we have the network addresses for LAN C and D, we can easily, and the start range for the unused section, we can work out anything in between that. and here's how we do it. So LAN A we've done here, 10.0.2.0, LAN B 10.0.2.128, and the start of the next range is 10.0.2.160 because we added another 32 onto it. So we can work out the broadcast address is 127, which is one less than the network address here, and the broadcast address of this range is 159, which is one less than the 160 here. And once we've got those, we can work out the host ranges easily, 2.1 and 2.126, anything between 2.1 and 126, which is between these two numbers here. Same with LAN B. Once we've done that, then the last thing we need to do is the WAN links. Okay, now the WAN links are these serial links here. Notice we only need two addresses, one for each end of the link, and we need one here and one here. Let's go back to our... So because we need two addresses, if we look at our table, that means we need two addresses here, which is going to give us 2 host bits. Okay, 2 host bits. That means if we have 2 host bits, then the remaining bits must be network, 30 of them. So that's a /30 mask, or in decimal 255, 255, 255, 252. Where do we get this number from? There's 255, that's the first 8 bits. There's another 255, that's 16 bits. There's another 255, that's 24 bits. And there's 30 bits there, because there's another 4 bits. If you add those up, 128 plus 64 plus 32 plus 16 plus 8, you will get the number 252. Notice the last binary one here is a 4. Okay, so that last binary one is a 4 in decimal, and that basically means that each of our networks is going to increment in blocks of 4. So this is our WAN address space before we subnet, and notice these are going up in blocks of 4, 3.0, 3.4, 3.8, 3.12, 3.16. We have a /30 mask for all of them because they're all the same size. That gives us a block of possible 4 addresses for each one. Remember, 2 are reserved for the network and the broadcast, so there's only 2 usable host addresses that can be assigned to either end of the WAN link. So we're conserving addresses here using VLSM. So we have only 2 WAN links in our topology. We've got HQ to site A and HQ to site B. So HQ to site A has a network address of 10.0.30/30, which is here. HQ to site B has a network address of 10.0.34/30, which is here. And from that we can work out the broadcast, which is one less than the start of the next range. So 10.0.33, 10.0.34 is the next one. The host range is the 2 numbers in between 0 and 3, so it's 1 and 2. And for site B, it's 5 and 6, which are the 2 numbers between 4 and 7. And we have unused space. These could be used for future WAN links if we need to, which are basically these unused addresses here. And there's 64 of those in total. We know there's 64 in total because we've borrowed 6 bits. We started off with a /24, and now we've ended up with a /30, and 2 to the 6 gives us 64 blocks of 64. When we've done this, we've actually finished our VLSM scheme. The last thing we need to do is assign the addresses to the interfaces and also the PCs. Now usually on a LAN, the PCs would be allocated via DHCP, and the servers and any router interfaces and switches will be statically allocated by an administrator. So basically these host ranges here, anything which has got host range can be a PC or a device can have one of these addresses. It can, as I said before, it cannot have the network and broadcast. So I hope this has clarified your understanding of subnetting. I would look at the other videos first and then have a look at this walkthrough. Try to practice out yourself using your own host requirements and see how you get on. And if you're getting really stuck and you don't understand anything, then just get in contact with me and we can go through it. Thank you very much, and thank you for listening.